So the first thing we need to understand is we need to understand, or just review, some of the history that we talked about that's related to what we'll talk about today. Okay, so reviewing really quick, de Broglie, our atom, okay? Keep in mind, once again, this was in 1924. That's less than 100 years ago this idea started coming about, okay? Can anyone remember for us, what does this fancy word quantized mean? When we say quantized orbitals or quantized wavelengths or quantized energy. I don't remember what that word means or the analogy we use when we say the atom was quantized.
Well, I know the analogy is like the ladder sideways.
Good, Brady. Yeah, so it's that, remember that energy or wavelengths are like a ladder. They're discrete numbers in which they exist. It's not all of them, okay? That's why when we looked at our spectrums from last time, with every atom, as the electrons fall, they're not going down a slide and emitting a full rainbow. If it was a slide, you'd see a full rainbow with everything. But they're emitting very specific rungs of the ladder. And then that's why we see lots of black and then very specific lines. Okay? Another one that's important with today's lesson is the Heisenberg uncertainty principle. So remember, this is the one that tells us it's impossible to know both the velocity and position of an electron at the same time. Okay? We talked about the analogy once again of if you're watching cars on the freeway, you can't be like, the car is here. Because as soon as you say that, it's not there anymore, right? And the same thing with electrons. And so then this led us into our modern view of the atom, which is from Schrödinger. Okay, so through Schrödinger's wave equation, we are able to calculate the probability of finding an electron. So once again, we don't know with certainty, but we can go on a range of probability, which we'll do a little lab next time, which will hopefully demonstrate this a little bit. Okay? All right, this is his equation. You need to memorize it and know how to use it.
No, tell me you're joking.
Just kidding.
Oh my gosh.
Like, don't you know what all these symbols mean?
Yes, that's the And that next one is one.
Oh, what? I know that one. I know pi. Okay, so with Schrödinger's wave equation, it is a quite amazing equation of what he was able to do. And if you choose to go and study chemistry further, you may learn how to use it, and it's quite awesome. But when we talk about orbitals in an atom, you could also call them our electron clouds. Okay, these are the 3D region of space where the electrons exist. Once again, recognize it's a probability that on this surface, this is our electron cloud, okay, there's a 90% probability of finding an electron there. We can see that in a probability distribution graph, where our x-axis is the distance from the nucleus. So as I get further and further from the nucleus, what happens to my probability? You get slower, right? The farther you get away from the nucleus, the less likely of a chance there will be that you will find an electron there. And we can get probability graphs for every different electron and their orbitals, okay? So the goal of today is, in a sense, or between today and next time, is we're going to be writing the addresses for electrons. Where are they located inside all of that space we talked about? So, because this is my life and it's just the way I work, so hopefully you figure that out. So I have another analogy for you as we talk about quantum numbers today. I do need to give a disclaimer that it is just an analogy, right? So it's not perfect. It's not really what's happening. But hopefully it can help you connect to these quantum numbers a little bit. But nonetheless, it was something that I came up with in a dream a few years ago. So the analogy I'm going to make as we talk about the atom today, okay, is we are going to pretend that an atom is like a hotel for electrons. Okay? So this is our electron hotel. So what we're going to want to be describing today is we want to be able to describe the floor the electrons are staying on and the room they're staying on, and then we'll get even more specific after that. Probably today we'll just get to floor and room, but we'll kind of see. And then what's cool is that periodic table is your map to the hotel. And we'll see how it connects, okay? All right, first quantum number is known as the principal quantum number. It's signified by the letter N. Okay, so n is the principal quantum number. And I put it on your paper, but according to our analogy, what does it represent? The floors, okay? So when n equals 1, what floor am I on? The first floor, right? In terms of the atom, this corresponds to the energy level of the electrons. Okay, so we have these different energy levels where they are, which also would mean it gives us an idea of the size of the atom. Because n equals 1, n equals 2, n equals 3, bigger and bigger and bigger, right? And you can see that here kind of in a picture, right? That 1 versus 3, 3 is a lot bigger energy level and size. So this picture right over here is a picture of our atom hotel. You can draw this on your notes if you want to. You don't have to, but if you want it to help you, feel free. Yes, it is a weird looking hotel. I know that. Okay, but it is an atom, and so they can do weird things, okay? So in our hotel here, this is the first floor. That's why it's n equals 1. This is the second floor, the third floor, the fourth floor, and technically, according to scientists, there's an infinite number of floors. We don't really know when it ends, right? Because really, they're not tangible things. They're just energy levels, but as far as we know, it goes to infinity. One thing, though, that you have to be careful with is the rows on the periodic table can tell us the floor that it's on. But the thing is that each block of the periodic table is numbered separately. Okay, each block of the periodic table is numbered separately. So don't be deceived by the numbers on the side. So like these numbers right over here, right, so it counts 1, 2, 3, 4, 5, 6, 7. Those kind of are the floors of the hotel. But you'll find that the periodic table is, the hotel looks shifted around compared to my picture up here. Okay? So we learned about the blocks back in Unit 1. That feels like forever ago, before I even knew who you people were, right? Does anyone remember, I guess maybe if you've looked below on the notes, the different blocks that we have? We have 4 different letters. There you go. Yep. So the 4 blocks we have are the S block, the P block, the D block, and the F block. So now we're finally going to talk about what these blocks mean. Right? We learned about them in the first unit, but this is really where they come into play. Okay, so notice, look at your diagram, or you can look at the one up here on the board. So every block has its own numbering system. Okay? It's nice, though, because the S block and the P block, they line up with the row they're on, right? If you just count 1, 2, 3, 4, 5, 6, 7, we see that those all line up with each other. But the D block, what's happened there? It's dumb. D block's for dumb. It's shifted down 1. Do you see that? Because the 3 is in line actually with the 4. The 4 is in line with 5.
Yeah. So there's no 7 for any of the D blocks?
As of right now, no. Yes. And then the F block, which actually I'll show you where it really fits, but the F block starts at what? 4. So there's actually a really nice pattern, though, even though it's weird, and we'll answer that question, Jeff, I promise, of why is it there. This, to be honest, drove me crazy in chemistry for a really long time, and it took me forever to like my junior year in college to get an answer of why is the D block not in line. Yeah.
Are you going to tell us why?
Yeah, but not today. But we will answer it, I promise. I won't leave you hanging till your junior year if you're a chemistry major. So, but what I want you to notice is this pattern, okay? The S's start at 1. The P's start at 2. The D's start at 3, and the F starts at 4. So there is a little pattern behind some of the non-pattern stuff, okay? All right, so first thing is we need to figure out what floor of the hotel it's staying on, okay? Now, on each floor of our hotel are rooms, right? It's a hotel, there's rooms there. Quantum number is known as the angular momentum quantum number, or the azimuthal quantum number. Okay? It's signified by the letter L, and we typically do like an italicized or a cursive L, so it doesn't look like a 1, but it's just L. Okay? This, in terms of the atom, are the sublevels inside the energy levels. So within n equals 1, there are sublevels, or on the first floor, there are rooms. But it is particular, okay? So the first floor of the hotel only has one room, and it's a 1S is what we would call that room. 1 being that it's on the first floor, and it's an S-type room. So I'm saying that there are 4 different types of rooms. The second floor of the hotel, because it's getting bigger, right, if you think of an atom, has a 2S room and a 2P room. The third floor of our hotel, we have a 3S, a 3P, and a 3D. That sounds like a fun room, right? 3D room. Get it? And then on the fourth floor, we have a 4S, a 4P, what the? 4P, 4D, and a 4F. Okay? All right, ready? Trick question. Show me on your fingers, how many rooms does the 5th floor have? Show me on your fingers, how many rooms does the 5th floor have? And I am telling you, it's a trick question. All right, Melissa, why is it 4?
It's 4 because there's only 4 blocks.
Yeah, do we have anything besides an S, P, D, and an F room?
No.
Not right now. Right, so actually the 5th floor looks the same as the 4. Okay? Does everyone see that? Because we don't have any other blocks, right? Okay? So then, okay, ready? Another question. Have a smiley face if you got the 4. How many rooms are on the 6th floor?
No. Also. Wait.
6.
All right, Justin, why is it 3?
Because F block doesn't have the 6.
Yes, look at our F block. We have 4F and we have 5F, but is there a 6F right now? No. Could that room exist eventually? Yes. But as of right now, with the biggest atoms we have, there's no such thing as 6F.
But there could be someday.
There could be someday. As of right now, that room is always vacant.
Let's go.
Okay? Are we kind of getting a picture here a little bit? Weird little picture? Okay. The cool thing is to this orbital, okay, depending on what type of orbital it is or sublevel, is it actually tells us the shape of the electron sublevel. So all S orbitals are spherical. If it's a P orbital, it looks like this. D orbitals, and then our crazy F orbitals. So these are the electron clouds of the different types of orbitals. So each orbital is unique in its shape. Okay? The values for L can range anywhere from 0 to n minus 1. So from 0 to n minus 1 are the ranges for L. Okay? And of course, oh, go ahead.
N can be infinite, so doesn't that mean the range could be infinite as well? Well, it would just be infinite minus 1.
Yes, but then minus 1 depending. But no, that's totally right, Brady. That's why we know eventually there could be a 6F, right? Because we're minusing 1, so that eventually they could be big enough to exist like that. Yeah. Okay, do you guys see that little table on there where it says like L equals? Do you see that in your notes? Okay, so what you need to recognize is, so these things are quantum numbers. So they have a number, but with this quantum number, we most often relate it to the letter. So that's what we're doing in the table, is connecting the number to these S, P, D, and Fs. And they just always match up this way. Okay? So when L equals 0, it's S. So when L equals 0, that's considered the S room, or the S subshell. Okay? When L equals 1, it's P. When L equals 2, it's D. And then when L equals 3, it's F. And that's all we have for now, right? Are just those 4 types of orbitals. So this is the quantum number, but this is how we'll often talk about it. We'll talk about it as an S orbital, or P orbital, or D orbital, or an F orbital. But that's the number that it corresponds to. Okay? Here's some other pictures of our different orbitals as well, just a different view.
How did
Okay.
you find out what the orbitals were?
So, I know I hate saying this, but next time I'll show you the device they use where they can, see. And a lot of it actually goes to Schrodinger's wave equation, that from his wave equation we can create
So it's like
these
equation?
pictures. Yeah, it's a mathematical equation where you can calculate the probability of finding an electron.
Man, that's great.
And from those equations, we get these pictures. Yeah, pretty cool. Okay, all right, ready? 4 smiley face, just somewhere on your paper. I'm going to give you an element, and this time, so you already gave me 1 quantum number, but this time I want you to give me 2. Okay, so for the element that has, let's do 6 electrons. Okay, 6 total electrons. Tell me what N equals and what L equals. So if it has 6 electrons and it's a neutral atom,
Oh.
what atom are you looking at? Carbon. So look at carbon on the periodic table. In a sense, what I'm asking you is to tell me the floor and the room is what I want to know. What floor and what room? What do you think, Melissa?
Isn't it N is 2 and L is 1?
Very good. All right, so help us know. So why is it N equals 2?
Okay, N is 2 because it's on this, like, the second, if you look at the P block, it's
Uh-huh.
on the second level.
Good. So carbon's on the first level of P, which starts at 2. And then how'd you get the 1?
And then 1 is, like, if you look at like the sub-levels, it says L equals 1 if it's P block, and it's in the P block.
So since it's in the P block, in a sense, we are in the 2P room. And numerically, P is always just for 1. Okay? So on one of your assignments tonight, it's going to ask you for these 2 quantum numbers. I'm going to give you the freedom where you can answer this question in 2 ways. You could either do this, where you do it as 2 and 1, or if you just want to write 2P, I'm okay with that as well, because they're the same. Gold, that's a good one. Let's do gold. Number 79. All right, write down either, you can do it like this, or like this for gold. Kim, what do you think?
5D.
5D. Who agrees with Kim? Hopefully all of you, because she is correct. Right, because remember D starts at 3, so we're counting 3, 4, 5, but we are in the D block. So what would be your L quantum number? 2, right, because 2 is always for D. Very good. Questions on our first 2 quantum numbers? Okay, let's introduce the next one, and then we'll be done for today. Okay, so our third quantum number, so we have floors, we have rooms. Inside the rooms of our Adams Hotel are bunk beds in these rooms. Okay, and it's very particular that they are bunk beds. Okay, so in our quantum numbers, it's known as the magnetic quantum number, and it's signified by M subscript L. So we call it M sub L, is how you'll hear me talk about it. Okay, what this quantum number tells us, so N tells us the energy level, L tells us the shape, and then M sub L tells us the orientation of the shape, because these things are in 3D. Okay, so pretend with me here that this balloon is a perfect sphere. because I can't make a circular balloon. Okay? Thank you. Okay, so this represents which type of orbital, S, P, D, or F? S, right? Because our S ones are the perfect spheres. Okay? How many different ways can we orient this balloon and it actually look different? I can turn it all different ways, but it's always looking the same? Yes. So it only has one orientation, right? Does that make sense? So in all of my S rooms, whether it's the 1S, the 2S, the 7S, there's always just one bunk bed. And that's a bunk bed. Okay? Because there's only one orientation. Okay. So this right here is a p orbital, right? Like the dumbbell type shape. Okay? So there are 3 orientations of the p orbital. If you want to think mathematically, you can have a p orbital that's along the y-axis, like so. You can have one along the x-axis, and then you can have one along the z-axis, which you've never talked about the z-axis. That's what makes it 3D. Okay? So a p orbital altogether, so if it has 3 orbitals or 3 orientations, that means all of our p rooms have how many bunk beds? 3, right? And when they fit together, I'm getting tricky here. So we have our y, our x, and then our z. Okay? So you can see, is there any room for any more orbitals in this right now? Not really. Yeah, so that's why, because a lot of people are like, well, why don't you have one like that's like diagonal on the x or diagonal on the y? And it's because, really, do orbitals want to be by each other? What's inside these orbitals? Electrons. And do electrons want to be by each other?
No.
They are all negative, right? Negative things don't want to be by other negative things. So we don't have any room for any more orbitals. Does that make sense? All right, then it gets a little crazier. The d orbital, I can't make this with balloons, I'm not that good, has 5 different orientations that it can actually become. Okay? So the d orbital can orient itself in 5 different ways, which means how many bunk beds are in d rooms? 5, right? So there's 3 bunk beds in our p rooms. You have 5 bunk beds in the d rooms. Anyone see a pattern?
7 in F.
How'd you do that, Brady?
We're just adding 2, starting at
Yeah, 1, 3, 5, 7. Right, so the F room, the fun room, has 7 bunk beds. Maybe that's fun, I don't know.
There's 14 people in one room, I don't know.
Some people that wouldn't be very fun. Okay?